Hello everyone and welcome back to another calculus video. In this video we are going to review parametric equations. So when we talk about parametric equation, we're writing how x and y are affected with respect to another variable, and usually that variable is t, and typically in real life it's going to represent time. So in the first example, we've got x of t equals t minus 1, y of t equals 2t plus 4, and t is bounded between -3 and 2 inclusively. We want to sketch what's happening with this parametric equation. So I like to start by creating a t-table. So I'm going to have a table with t values, and then x values, and then y values. My t values are limited from -3 to 2. So -3, -2, and -1, 0, 1, and 2 is what I'm going to use. And then we're just going to plug these values in, and that's going to give us an ordered pair out, and then we can graph that ordered pair on the Cartesian plane. So if I plug in -3, I'm going to have -3 minus 1, which is a -4. And then if I plug -3 in for the t value in y, I'm going to have 2 times -3 plus 4, which is going to give me a -2. So my ordered pair out would be -4, -2. When I plug in -2 for x, I'm going to have -2 minus 1, which is a -3. If I plug it in for y, I'm going to have 2 times -2 plus 4, which is a 0. And then we're going to do the same thing for each of the rest of these. When I plug in -1, -1 minus 1 is a -2. 2 times -1 plus 4 is a +2. 0, when I plug it in, is going to give me a -1 and a 4. When I plug in 1, 1 minus 1 is 0. And then 2 times 1 plus 4 is 6. And then when I plug in 2, 2 minus 1 is 1. And then 2 times 2 plus 4 is 8. So I'm going to draw my Cartesian plane. And this is just going to be a rough sketch. It's not going to be to scale. Each tick mark is going to represent 1 unit. So I'm going to label a few things on my axis. And then we're going to plot the dots. So my first ordered pair is -4, -2. And then I have -3, 0, -2, +2, -1, 4, 0, 6, and 1, 8. And you can see what's coming out is this linear function, but what's nice about this is that we can tell how the graph is moving. We started with this point in the third quadrant, and you can see it's moving from left to right. So it shows orientation, and those little arrows there are important to me because it shows how it's moving. Now, if we wanted the equation that models this, if you think back to when we did this in our trig class, x is equal to t minus 1, y is equal to 2t plus 4. We could solve one of these equations for the variable t and then plug it into the other one. So I'm going to do that. I'm going to solve the x equation for t. So I'm going to have x plus 1 equals t, and now I have a substitution that I can plug in here. So y equals 2 times t, which is really x plus 1 plus 4. So I'm going to have 2x plus 2 plus 4, which is 2x plus 6. So if I wanted the xy equation, this line is represented by the function y equals 2x plus 6. But it's not the entire function because it's just a segment of it. Remember, we restricted t here, so we would want to put a restriction on the x values here. And you can see that our x values are bounded from -4 to 1. So this equation works as long as x is between -4 and +1. So let's look at the next one. X of t is equal to t squared minus 3, and y of t is equal to 2t plus 1, and t is bounded between -2 and 3. So I'm going to copy that down here. This is example 1, part B. X of t equals t squared minus 3. Y of t is equal to 2t plus 1. And t is bounded between -2 and 3, and that is including both the bounds. So this is where you may want to try it. Pause the video, come back and check your answer. So t, we're going to have -2, -1, 0, 1, 2, and 3. When I plug in -2, I'm going to have to find x. It's going to be -2 squared minus 3, which is going to be a 1. When I plug y, I'm going to get 2 times -2 plus 1, which is -4 plus 1, which is -3. Then we're going to plug in the -1. So -1 squared minus 3 is going to be 1 minus 3, which is a -2. When I plug in to find y, it's going to be 2 times -1 plus 1. So that's -2 plus 1, which is going to be a -1. When I plug 0 in, I'm going to get -3 and 1. When I plug 1 in, I'm going to have 1 squared minus 3, which is -2. And then for y, we're going to have 2 times 1 plus 1, which is 3. When I plug in 2, 2 squared minus 3 is a 1. And then 4 plus 1 is going to give me a 5. And when I plug in 3, 9 minus 3 is 6. And then 6 plus 1 is 7. And then just like before, we were going to graph that on a Cartesian plane. I'm going to draw tick marks again. So let's look at our points on our plane. I've got the point 1, -3. -2, -1. -3, +1. -2, 3. 1, 5. And then 6, 7. So it started down here in the quadrant 4 with the point 1, -3, and it's moving to the left, and then it's coming up. Okay, so we can see orientation, how this is moving along the path. We could think about this like a path. And in Calc 3, you're talking about paths in terms of line integrals. And notice I did not extend. It's a sideways quadratic opening to the right, but I did not extend because t is limited from -2 to 3. This path stops in the fourth quadrant and the first quadrant. So what if we wanted the equation? We could do the same thing we did before. We're going to solve one of the variables for t, and we're going to plug it into it, the other equation. So in this case, I'm going to, because it's an opening sideways quadratic, we know this is going to be in the form of x equals. This is not a function that fails that vertical line test. So I'm going to solve the equation, the y equation for t. I'm going to subtract 1, divide everything by 2, and then I'm going to plug that in for my t in the x equation. So x equals t squared minus 3. t is going to be y minus 1 over 2. So there's my equation that's modeling this. And if I wanted to, I could, FOIL some things out here, put it in standard form for quadratic. I'm just going to leave it. Part C was looking at one in terms of sines and cosines. We had x of t is equal to 4 cosine of t, and y of t is equal to 4 sine of t. And we're looking for t to be bounded between 0 and 2 pi inclusively. Now, if you remember back to pre-calc, this is actually going to form a circle. And we're going to graph a few points, and I'm going to graph some of the nice points here. So I need a t column, an x column, and a y column. I'm going to look at 0. We'll look at pi over 2, pi, 3 pi over 2, and then 2 pi. That way we can get orientation. So if I plug 0 in, I'm looking at 4 cosine of 0. Cosine of 0 is 1. So my x-coordinate is going to be 4. The y-coordinate is going to be 4 sine of 0. Sine of 0 is 0. So the y-coordinate is 0. At pi over 2, I'm going to have 4 cosine of pi over 2. Cosine of pi over 2 is 0, so x is 0. The y-coordinate is going to be 4 sine of pi over 2. Sine of pi over 2 is 1, so the y-coordinate is going to be 4 times 1, which is 4. At pi, we're going to have 4 cosine of pi. Cosine of pi is negative 1, so my x-coordinate is going to be negative 4. The y-coordinate is going to be 0, because we know sine of pi is 0. At 3 pi over 2, so at that moment in time, my cosine is going to be 0, so x is 0, but sine of 3 pi over 2 is negative 1, so this will be a negative 4. And then at 2 pi, we're going to have cosine of 2 pi, which is 1. And 1 times 4 is 4. And sine of 2 pi is 0. So if we were to graph this, I'm starting at the point 0, 4 over 0. Sorry, I'm starting at the 4.40. I read that backwards. So over 4 up 0, positive x-axis there. And then I'm moving to 0, 4, which is here. And then I'm moving to negative 4, 0. And then I'm moving to 0, negative 4. And then back to 4, 0. So this thing is moving in a counterclockwise position. Let's say we want to find the equivalent equation in terms of x and y only. So we know x is equal to 4 cosine of t, which means x over 4 is equal to cosine of t. And we know y is equal to 4 sine of t. So y over 4 is equal to sine of t. And then we can relate these using the Pythagorean identity. Sine squared plus cosine squared is equal to 1. So we have y over 4 squared plus x over 4 squared is equal to 1. So y squared over 16 plus x squared over 16 is equal to 1. Or we could write this as x squared plus y squared is equal to 16. So there's our circle centered at 0, 0 with a radius of 4. So we've talked about graphing, we've talked about orientation, we've talked about converting back to a rectangular equation from a parametric equation. Let's look at a couple more of those. This is where you may want to pause the video, try it, and then come back and check your answer. So in example 2, we want to eliminate the parameter. We want to write this just in terms of x and y. So x is equal to square root of 2t plus 4, y is equal to 2t plus 1. T is bounded between -2 and 6 inclusive. So we've got a few options. What I would want to do is solve this y equation for t. So I'm going to subtract 1 and divide by 2. And then I'm going to plug it into the t for the x equation. So x equals the square root of 2 times y minus 1 over 2 plus 4. And then we're going to simplify this. So this 2 and this 2 is going to reduce. So I'm going to have a y minus 1 plus 4. And that's under the radical. So this is going to be a y plus 3. And then if I square both sides, I'll get x squared equals y plus 3. So x squared minus 3 is equal to y. There's my rectangular equation. But now we've got to figure out where is this equation good? Because for a quadratic, we usually think about domain all real numbers. However, since the original function was restricted between -2 and 6, then this needs to be restricted as well. So let's look at that t-table. -2, -1, 0, 1, 2, 3, 4, 5, and 6. So there's my t's. And then I need a column for x and a column for y. So we're going to take a minute and we're going to fill that table out. That way we can get an idea of what this looks like between the t-bounds of -2 and 6. So take a minute, pause the video, and fill it out. So when I create my t-table, some of my x values are going to have square roots. I'm just going to graph the nice ones. So 0, -3 is my starting point. And then I've got the nice 0.21 and I've got the 0.413. So I can see that quadratic coming out. We know it's a quadratic because we solved it in terms of just x and y by eliminating the parameter t. I can see orientation from the graph. I can also see the smallest x value is at 0 and the biggest one is 4. So this equation works as long as 0 is less than or equal to x, which is less than or equal to 4. So there's that parameter. We can do the same thing for example B. This one's going to be an ellipse. So this is example 2, part B. X is equal to 4 cosine of t. Y is equal to 3 sine of t. So like before, I'm going to solve for cosine and sine. So x over 4 is equal to cosine t of t. Y over 3 is equal to sine of t. And this one is looking at the graph from 0 to 2 pi, I believe. Yes, 0 to 2 pi. So let's start by eliminating the parameter. We need something that relates this together. That's our Pythagorean identity. Cosine squared plus sine squared is equal to 1. Cosine is x over 4. Sine is y over 3. So I've got x squared over 16 plus y squared over 9 is equal to 4. So there's my equation of my ellipse. I could draw that. I could create a t-table. See if I can do that here. I have x's, y's, and t's. Let me scoot that over. So I'm going to start at 0, look at pi over 2, pi, 3 pi over 2, and 2 pi. So this is where you're going to want to pause the video, finish the table, come back, and then we'll check your answer. So when I create my table, I get the list of x and y ordered pairs, and when I plot those, I start with the point 4, 0, and then I move to 0, 3, then negative 4, 0, then 0, negative 3, and then 4, 0 again. So we can see this is moving in a counterclockwise position. If I wanted to talk about bounds for x and y, I could. We can see x is bounded between negative 4 and 4, and y is bounded between negative 3 and 3. The last thing we're going to talk about is parameterizing a curve. We're going to find two different pairs of parametric equations that represent the graph. Y equals 2x squared minus 3. So we're trying to parameterize this quadratic. We know the domain of this quadratic is all real numbers. I can plug anything for x, and then I'm going to get out a specific set of y values that look like 2 times the x squared minus 3. So one way we could parameterize this is we could say x is equal to t, and then I'm going to make that substitution. So y equals 2 times t squared minus 3. And that's going to have the same outcome. X could be anything here. And then that anything is going to help us describe y in terms of what we chose for x. Another option that we could do is we could say x could be equal to t cubed. So then y would be 2 times our x squared minus 3. So it's going to be 2 times t cubed squared minus 3, which is 2 times t to the 6th minus 3. And this is going to produce the same graph. This works because x can still be anything. If I plug in negative values, I'm going to get out negative numbers. If I plug in 0, I'll get 0. And if I plug in a positive 1, I'm still going to get out positive numbers. So the domain for x here is all real numbers. And there's an infinite ways that you can do this. Another option we could choose is say, what if we want x to be 5t plus 2? Then y is going to be 2 times our x squared minus 3. X is 5t plus 2, and then we could simplify that, and that's going to produce the same set of equations there. The graph will look the same. Here's what we cannot do and what we have to be careful of. Letting x equal t squared will not work. The reason, think about what we could plug into x in the original. We could plug anything into x. Same thing here. We can plug anything into x, and we will get out everything from negative infinity to positive infinity. If we say x is equal to t squared, we have limited what x can be. In this case, x can never be negative. So that's a huge issue because then we can't get the same graph that we had before.